Is the font big enough for everybody?
Yes, yes, it looks fine.
Yes. Okay. So what we want to write, we can say we can look at our shader. So let me make this one a little bit larger so that we can look at okay, our shader, and we can see that the output name is called output color. So I just take that one as output color, copy it here, and then there is a property location that we will talk about in detail later on. But the target that we are going to use is that output texture. And that completes the definition of the texture that we had over there. And if we do that, now we will see that nothing is written to the canvas that we were using anymore. So in order to visualize now this texture is we can use some of the plotting algorithms that we have. So we can define this plotting algorithm plot that uses one of the libraries plotting tools, plot2D, and the target that we want to plot is this output texture that we used over there. We want to plot the red channel of it, and we can choose some minimum value and maximum values for that channel. So let's say we start from 0 and we go all the way to a maximum value of 30, and we put a color bar that we are using at the bottom so we can know what are the values representing, and the canvas that we are going to use for plotting would be canvas 1. Okay, and if we are done with that, we can initialize the plot.
Is it a typo? Should channel have 2 ends, or is that what it is there?
I think as I was developing the library, I put it with 2 ends. And later on, I fixed the typo, but if you use 2 ends or 1 end, both of them should work. So I kept the 2-end version just as a legacy. Okay. So if we want to plot everything, we have to make sure that we render the plot as well. So let's define a function. We can define a function that does discard, solving, and visualizing. Solve and visualize, and probably visualize. And the definition is basically running these 2 functions in sequence. So if now I run the function, solve and visualize, it should try to visualize that. Okay, so now that we have that, we can play around with our coloring scheme a little bit. Remember that we talked about that we can do a little bit of coloring. So instead of returning 0 there, we can just break the loop. We can remember how many iterations it took for the Mandelbrot set, or in this scenario the Julia set to exit, and at each level we can remember what iteration we were in, and we can use the iteration here for our coloring. Log of length of our Z number probably shows that divided by log of 2. Right now all the channels are the same number, and if you do that you get this nice coloring of the Julia set. Okay, so basically what's happening is right now everything that we are calculating here is being written into this 2D matrix that has RGBA values, and its size is 512 by 512, and each pixel is being stored into this data structure. The value that is here is, I would like to mention that this is residing over the GPU. This resides on the GPU. Okay. So the next concept that I'm going to talk about is the concept of interaction. So one part that you need to remember is that this part that we are defining here is basically these are all CPU code. So everything that we have here is CPU code on the JavaScript side. And everything that we have on the shader side is GPU code. On this side we have GPU code. And GPU code and CPU code, they have two separate parts for handling the memory. The GPU code, the CPU code has access to CPU RAM, and each GPU has its own memory, and the processes on the GPU access their own unit of memory. So if I wanted to send part of this information into the GPU, it should be through some sort of intermediary variable that should be copied over there. And those variables are called uniforms. So I can define a uniform variable, let's say R, and I can define another uniform variable named theta. We're defining, for example, this variable constant that we are adding here. So instead of that, we can now sending two variables there. So remember what we had over there. I can change it to R and theta for the moment, just as it is. And before I add R and theta, you can see that if this was 0 and 0, the shape that I would get would be a circle, right? Anything outside the circle would basically diverge to infinity. Anything inside the circle would remain bound. And if I changed it to R and theta here, it seems that the initial value that they take is just 0. So if I wanted to define something and send it from the CPU code, I have to send it through this uniforms section in the solver. I can say that I want to have an R value. That is, I have to pass the type of it, that is a float, and the value that I want to send over. Let's say the value is minus 0.9 that we had before. and then a theta value that we want to send also is float, and we want to send a value of 0 to it. And we need to close that. Okay. So basically now this R value and theta value will be sent over to the GPU. Unexpected thing. Quickly go to the.
You need to put a colon between type and string F for R.
Yes.
Yeah, you need only a 1.
Yes, thank you. You can see the number is passed to the GPU now from the CPU side. So we are sending a number to the CPU side. So later on, if we change something, let's say I wanted to change that one to -1, I could use the renderer, access its uniforms, and the R value that R uniform that I had over there, and change its value to, let's say, minus 1, minus 0.5, so that we get something different. And then when I render it, now it should use the new value that we passed over there, and we get a new value over there. So one way to change these uniforms is through a graphical user interface. So to add a graphical user interface, I have forked a library called DAC.GUI. It's part of this library as well right now. So in order for it to work, the variables that you want to add to the graphical user interface should be put into a structure. So I define this R value, let's say, I call it R. I call it radius on this side so that we see the difference. Radius as -0.9. And some sort of theta here as 0. To define a graphical user interface, we can create a GUI by calling on this GUI. Creates a new GUI, and to the GUI you can add panels. So I can define a new panel by adding a panel to the GUI. And if you do that, you should see some controls being added there into the code. And the nice part about this library is that it's very easy to add variables to the panel now. So in order to add, I can say from the environment, I can add radius to the panel, and it will automatically add a radius part that I can change here. Okay. So this radius is being added here, but it's not connected to anything. What we can do is we can say that what we want to do whenever this value is changed. So on change, we want to run a function. You can see you can type in console log environment radius. So this is for debugging purposes. You add it there, you can see as I'm changing it, the new value is being displayed there. But what we need to do is basically, first we need to tell our solver like here that we were changing the uniform, we want to tell it that the new value is ready and send it over. So instead of this R, I send environment radius over. And when we do that, we have to visualize our solution again. We have to solve so that the renderer renders the solution again. And we're going to start plotting a new value over there. So this unchanged part is the important part that we need to remember that we add there. So it is very smart. You can add minimum values. Say that you don't want to go below, I don't know, -2, and a maximum value of 2. And if you do it like that, it will automatically also add something here so that you can change it like so. If the values are booleans, it will automatically change into a checkbox. If the value is a function that you are sending here into the library to be added, it will add a button over there, so you can change a lot of the stuff.
So I was trying to figure out how to do a slider.
Sorry?
Have you figured out how to
Slider?
add a slider? A slider.
This is a slider.
A little slider.
Slider?
Yeah, well, actually, well, that's true. That's a slider. Yeah, okay. Yeah, that's
This is
a slider.
by definition a slider.
That's right. All right, that's a slider. Okay, I'll shut up. Okay.
Exactly what I added. Have you figured out?
Thanks.
Yeah, you can do it with data as well. So we add the data so we can do the same thing, unchange here on a function. And function is basically, and copy that line, paste it here. And here we want to change the theta value, and the new value would be the new value of theta. And you want to visualize everything again. Now we can have a second value that we are changing, and probably you know that this is of the type that you usually have cosine of theta here and sine of theta. The reason I chose to do this part is that you can see that you can do vector operations. You can multiply a scalar by a vector and it will automatically take care of those operations for you. One thing that you can see here, the angle theta is right now changing by integers. So what you can change here is by changing the step size and saying that this changes by 0.01. Do it much more smoothly. A lot of the functions that you have here can be also changed. For example, in the plotting algorithm, you can see that we have a max value over there for the plot. You can add a max value here. There's like 30 value that we had over there. You can add it to the and here what you need to change is actually for the plotting we want to change it a little bit. So plot max value, actually max there. You should remember to initialize your plot so that the color bars also change. I think it automatically does it, but I don't know. Start playing with this number. And start to see different things. So a lot of these features that are there can be changed like that afterwards, after the fact that you define them. If it is necessary, right now I'm changing them through the graphical interface. But if you have a need to change them via scripts, you can do that as well. So the important part for this session is to remember this concept of uniform variables. And the reason that they are called uniforms is that they are uniformly defined all over the domain. So for each and every fragment, they are uniformly defined as these values. The other types of uniforms that we can have, we will see them later, that these textures can be actually used, that we defined here. The textures can be used to be used as a means to create time stepping to solve problems that involve time stepping. And they can be used as input to other solvers, and they can be used as output to solvers. One other part that we will see later on, this was this location feature that I used here. And there actually can be something called here as layout, that you can use this location. We started from 0. We can have actually multiple color outputs. So if I wanted to have a second color over here, I don't know why it's treating this one as a comment, because I deleted the comment. So there can be an additional color that we are calculating here. So you could have this texture here and another texture, or a second set of colors that we could calculate. And here you could have the second set. So the name that you see on the left-hand side is just for references, so that you can see it's actually what it's using is these numbers for the locations that are the important part. So you can have something completely different calculated for the output color 2 here. So for example, if the length of if our distance from the center was less than 0.5, 0.2, let's say, you can set out color 1. I think I used out color 1, vec4 of 1, else color 1 to be vec4 of zeros. Pixel.
I think on line 32 you need to open a comment. Yeah.
Yeah. I think it was output of the shader or pixel color was the continuation of that. Okay. Right now you're seeing that still we are visualizing output color 1, but you could visualize output color, the second color that we calculated. If you do that, you'd see that we are drawing a circle that outside of it was 0, inside of it we were calculating 1. So this is useful that you can go up to 8 colors here, 8 sets of colors. So if you are in a position that for each pixel you want to calculate multiple colors, you can do that. What is that useful for is that if, for example, you have a cardiac model that you wanted to simulate that had more than 4 state variables, then RGBA colors that could be assigned to that. Let's say you had some sort of calcium dynamics, sodium dynamics, you could start adding more and more here. Right now you can go up to 8, so 32 state variables can be calculated in one shader alone. And then we will see later on how we can have multiple shaders to take care of the colors, to take care of models that have more than 32 state variables.
So a couple of questions.
Sure.
So what's the difference? You're using the keyword layout and then a location. Is there some meaning for those? I mean, why not just use out? What's the difference between doing that and just saying out?
Oh, this layout word is a keyword that you can assign different locations on the GPU. In the background, a lot of stuff is happening. And if you have just one out, it would assume that you are using location 0 for that. But if you have multiple locations, or basically you want to calculate multiple colors, is when this thing can come into the picture. And the syntax is like that. I don't remember what are the other layouts that you can use. But I remember, what I know is that you can, if you saw the first part, where we were talking about the vertex shaders, you can have multiple outputs from the vertex shader as well, and these layouts can be useful into accessing those ones quickly. The location part is also another way to quickly set up everything. These numbers, by the way, can be in different orders on the shader side. But for some reason, if you mess up with the order on this side, on defining the solver, I wasn't able to set them correctly. So they would require you to go through an ascending order, starting from location 0 and to location 1 and proceed as such on this side. I could do a sorting later on, but I didn't do that. I guess you could read these ones and then sort them based on the location part.
Okay, so if you only have one out, if you only have one thing that you're outputting, then maybe you wouldn't need the location.
You wouldn't, yeah. If you had just one color output, then you wouldn't need the location.
Okay, or the layout command.
Yes.
Okay, all right. Thank you.
I just want to make sure I understand something. The max value that you're setting, I can see that's used to determine like the color map, but it's not used in the shader code itself. So is the plot command actually recoloring everything based on the values in the texture, or was I just missing something?
Okay, so let me share the screen again. So you can see the color map that we have here. I think it wasn't showing it here. It's the minimum value is 0 and the maximum value is right now 30. If you were directly plotting to the canvas, the values could go only from 0 to 1. So if you want for each of these color sections that you were calculating, for color channels that you are calculating. So if I had a canvas here and I was directly drawing to the canvas, for each one of the channels, the colors would be bound between 0 and 1. So you are in charge of actually setting up what is the appropriate values. But when you're writing to textures, actually you can output any float value to the texture. It's just the data structure, and these are the numbers are considered to be intermediary calculations that do not necessarily represent a final color to be shown on the screen. But what the plotting algorithm does is that it maps one of these channels to the color map that we have over there. We can have different color maps as well, so you can change it to that rusty jet that is used in MATLAB, for example, and it will change the color scheme, that jet color that you have seen in MATLAB. It actually has a lot of color maps available by default. Go to the plot and you say, color map list. And if you run that, there is a long list of color maps that you can use. Default, it has one, I think it was 77 color maps. You can use it for different purposes. The most important part is that you want to be able to carry out your computations without bothering to scale your values between 0 and 1. You want to be able to have negative numbers, positive numbers, whatever you want to do if you want to do numerical computation. So that's why we have separated the plotting from the rest of the stuff.
Yeah, that totally makes sense. Thank you.
You're welcome. Any other question? No?
This might be getting ahead, but can you do animations?
Yes. So basically, the next thing that we want to do is actually we want to be able to have time marching simulations like this one. You have a solution, there's marching, you can interact with it, create a new simulation. And later on, we will go into 3D calculations. You can have either for example, for example, one of the cardiac models on a 3D structure. So I think in 2 weeks' time, we'll reach the time that we will be able to calculate 3D structures. So whatever wish list that you have that you want to go through, please put it in the list so that I can start preparing for what we can go through. One of the things that Flavio mentioned was that he would like to see, for example, interactions of these codes with something like a Python code, for example. How can you interact with the Python code, send information back and forth, or any other code? Or you want to be able to send, for example, a time series to MATLAB for post-processing, either as dumping the data or sending it as a live simulation into MATLAB, that the MATLAB simulation or program is handling this data, making some decisions, sending back some sort of information into the program to decide to do what it wants to do. So all of these stuff are possible, but please let me know which ones you are more interested. What are the questions that comes to your mind? so that we can prepare having stuff on those topics.
Thanks, Abusar.
Yep,
You're
thank you.
welcome. I think
Yeah, thank you.
All right.
So,
Could I